Welcome back to this channel. This is the first video on a closer look physics series. In this video, we shall take a closer look at concepts such as speed, velocity, and acceleration. So let's get started. Let's first talk about speed. Speed is a measure of how fast something moves, or more accurately, how fast an object covers a certain distance. Let's assume you have an object that is moving along the x-axis, as shown. So it moves all the way until it gets to a certain point. Let's call that point A. It is a distance, say 10 meters away from the origin. Assume the object takes 2 seconds to cover that distance. Then we say speed of this object is quite simply the distance it covers over the time it takes to cover that distance. So 5 meters per second. So this is how fast the object moves. Note, in describing the speed, we do not care about direction of motion. That information is contained in velocity. Velocity addresses how fast an object is moving and in what direction. Coming back to the earlier example, let's assume we want to determine the velocity of this object. It is given by the displacement of this object in traveling from origin to point A over the time interval it takes to cover that displacement. In this case, the displacement is 10 meters to the right, where I hat is the unit vector along the positive x-axis direction. Divide that by the time interval 2 seconds. You get the velocity as 5 hat meter per second. So velocity is a vector and speed is a scalar. Now let's look at another motion. So you have this object. It first moves to point B, and then it reverses and stops at point A. The question is, what is the speed and what is the velocity of this object? Well, that depends. Note, as the object takes off from the origin and it moves rightward all the way to point B, let's assume the object is here, and its speed is, let's say, v at that point. And then it moves, and by the time it gets to point A, the speed is something else. Let's call it VA. And then as it moves along and gets to point B, before it reverses its direction, it has to come to a complete stop. So at that point, the speed is quite simply 0. Such speeds are known as instantaneous speeds. They describe speeds at a particular point. For example, VA is speed when the object is at point A, VB is the speed when the object is at point B, and so on. In this process, many things can happen. The object can simply speed up all the way to point A and then slows down and gets to rest as it gets to point B, and then it reverses, speed up all the way and halfway slows down and get to point A, and then it stops there, for example. Or it can still just go all the way with constant speed until it gets to point B, and then it stops there, and then it accelerates and gets to some constant speed and then slows down and gets to point A. That could also happen. If you don't want to concern yourselves with all the details of the motion, and let's say you're looking for a single number that quantifies the speed of this object as it takes off from point O and comes back to point A, that single number is reflected in the so-called average speed. The definition of average speed is quite simply the total distance traveled by the object over the time interval, or the time it takes to complete that distance. In this case, let's say the distance between O and point A is x1, the distance between point A and point B is x2, then the total distance it travels is x1 plus x2 plus x2. x1 plus x2 and another x2 as it goes from B to A. And the average speed is quite simply that sum divided by the time it takes to cover that distance. And that is how we calculate the average speed. So let's say A is 5 meters away from origin and B is 4 meters away from point A. Then the average speed is 5 plus 4 plus 4. Let's say it takes 3 seconds to complete the journey, divide by 3, which gives an average speed of 4.3 meter per second. And of course, since speed is a scalar concept, it says nothing about direction. Now let's calculate the average velocity. As we have seen, average velocity is given by displacement of the object divided by the time it takes to cover that displacement. Displacement is a vector. So by definition, displacement vector equals the final position vector divided by the initial position vector. We note the object starts from 0, so that means the initial position vector of this object is 0 I hat meter. The object stops there after completing the journey. So the position vector of point A is the final position vector of this object. So in this case, it is 5 I hat meter. Positive I hat because point A is to the right of the origin. So substituting this information, this displacement is 5 I hat minus 0 I hat. Let's say it takes time 3 seconds to complete the journey. You get 5 over 3 I hat meter per second, which is about 1.67 I hat meter per second, which is different from the average speed that we have calculated earlier. In this example, we see the magnitude of the average velocity is 1.67 meter per second, whereas the average speed that we have computed earlier was 4.3 meter per second. Sometimes, depending on cases, the average speed is the same as the magnitude of average velocity. However, the two can be quite different, as shown in this case. Next, let's look at acceleration, which is a vector. Acceleration, by its definition, measures the change in velocity over time. So let's look at this figure. Let's assume you have an object. It moves all the way from the origin to point C. Let's assume it speeds up, namely its velocity increases with respect to time as it moves from point O to point C. Then we say the acceleration of this object is positive. In other words, the object is accelerating. Now let's assume it moves to point A with ever-increasing velocity, and from A to B it slows down, and then it speeds up again as it gets to point C. So from O to A, the acceleration is positive. From A to B, the acceleration is negative, or the object is decelerating. And from B to C, the acceleration assumes positive values. Let's assume you demand the value of acceleration vector exactly at point A, or at point B, or anywhere exactly between B and C. So these acceleration values at a particular point at particular time are known as instantaneous acceleration. In contrast, despite the complication and details and variation of accelerations all the way, we can always write down a single number that denotes the acceleration of this object. It is known as the average acceleration. And the definition for this average acceleration is, say that we are interested in acceleration between O and C, is simply the velocity of this object at point C minus the velocity of the object at point O divided by the time it takes to achieve such a change in velocity. So this single number can be used to represent the acceleration of the object from point O to C on average, despite the complication of the motion. Let's look at the following problem. At a certain time, an object has a speed of 20 meters per second in positive x direction. 3 seconds later, its speed was 40 meters per second in the opposite direction. Find the average acceleration of the object during this 3 seconds interval. So the average acceleration is computed using the final velocity minus the initial velocity over the time interval. The final velocity is 40 meters per second in opposite direction. So 40 opposite direction is minus I hat, because originally the object was moving in a positive x direction. The initial velocity is 20 I hat. The time interval is 3 seconds, which will give you minus 20 I hat meter per second squared. Let's look at this problem. A car is driven from A to B half the time at 15 meters per second and half the time at 25 meters per second. On the way back from B to A, it travels half the distance at 15 and another half the distance at 25. What is the average speed of the car from A to B? Let's say this is half the time, so 15 meters per second, and the other half the time is 25 meters per second. So the total time is, let's say, delta t. So the time interval for the first segment is delta t over 2, delta t over 2. Let's say this distance is x1, that distance is x2. So the average speed from A to B is the total distance, which is x1 plus x2 over delta t. So what is x1? x1 is the speed for that segment, which is 15 meters per second, times the time it takes, which is delta t over 2. Likewise, x2 is the speed for that second segment, 25 meters per second, times the time it takes, again, delta t over 2, over delta t. So delta t goes away, and the answer you get is 20 meters per second. So that is the answer for part A. Now let's look at part B. What is the average speed as it goes back from B to A? Note that on the journey back, half the distance is traveled at 15 meters per second, the other half is 25 meters per second. So the distance are the same. Let's call it x and x. So the average speed on the way back is the total distance, which is x plus x, over the total time interval. Let's say the time interval for the first half is t1, the time interval for the second half is t2, so it's t1 plus t2. So it's 2x over, what is t1? t1 is time it takes to go from here to here. And that is, quite simply, the distance x over the speed 15. So x over 15. Likewise, the time t2 is the same distance x over this new speed 25. So x goes away, and the answer turns out to be 18.75 meters per second. Part C. For the entire trip, what is the average speed? So for the return trip, the average speed is the total distance traveled. The total distance is, let's say this is x, that is x, that is x, that is x. So it's 4x altogether, over the total time it takes to go from A to B. If you recall, that was delta t, plus the total time it takes to go from B to A is t1 plus t2. So first let's determine delta t. Delta t, which is the time it takes to go from A to B, equals the total distance, which is 2x, over the average speed for that motion, which we have worked out in part A, and that is 20 meters per second. Likewise, t1 for that return journey, that part of the return journey, equals the distance of that part over the speed for that journey, which was 15 meters per second. Likewise, t2 is the remaining distance over the speed for that part, which is 25 meters per second. So putting this in here, and that in here, you see the x's will cancel, and you will get 19.35 meters per second for the average speed for the entire trip. Now part D, what is the average velocity of the car for this entire trip? The average velocity equals displacement over the time interval. However, the car starts from here and ends up there, so that means the displacement is just 0 over time interval. So you get 0 meters per second for the average velocity. And as you can see, the magnitude of that average velocity is different from the average speed. And they need not be the same, as we have stressed earlier. Thank you for watching.